Good afternoon. My name is Camilo, and this work, Automatic Library Categorization, is in collaboration with Coen De Roover. We work at the Software Languages Lab from VUV in Belgium, and in case you want to reach us, we can share our contacts later on. The scope of this work is library categories. So, what are those library categories? Basically, a generic name for a group of libraries with common functionalities. Imagine you have three libraries, A, B, and C, and A and V share some common functionalities, so they are grouped together into the category X. In addition, B and C also share some common functionalities, and they are also placed together into another category Y. As this simple example shows, several categories could be made from several libraries, and one particular library could be part of several categories, such as library V in this case. Real-world examples of library categories could be found on the Maven software ecosystem, where you can have aspect-oriented actor frameworks, application metrics, and so on. Also, you can find examples of library categories on the Scala library index and on the GitHub tags. Library categories could support software ecosystem exploration only if they cover all the libraries on the software ecosystem or the majority of the libraries on the software ecosystem. For example, on the Maven software ecosystem, out of the 70,000 libraries reported by Badri and collaborators, only 38,000 of them are categorized. As a second example, new libraries incoming into the software ecosystem, as the snapshot on your right shows, they do not have any category on them. So basically, our approach targets this problem to categorize uncategorized libraries on the Maven software ecosystem and to categorize new libraries incoming into the Maven software ecosystem. And it basically consists on two major phases, one training phase and one labeling phase. As a general overview, our approach of library categorization is based on a text classification approach. The two phases, training phase and labeling phase, contains several steps. Specifically, the training phase is responsible for gathering all the information from the official website, transform this information into vectors, and finally train machine learning models on this information. The labeling phase is responsible to put a category to a new library, and finally the output of these phases is going to be evaluated with classic techniques such as precision and recall. I'm going to explain now into details in what consists the training phase. The training phase consists on several steps. The first one is to collect the information from the NVM repository or the official Maven website. What we did is to collect for each library into consideration the category of that library and the artifact or jar file from that library. And that's basically the information that we gather, jar files and each of the category per library that we could extract from the Maven software ecosystem. With only the jar files of the libraries, we use the visual library to extract the names of the classes and the names of the methods on those jar files. And we process the bytecode of those jar files. For example, for the more files class on your right, consisting of 4 methods, we basically collected the name more files and the names of all the methods on that class. We did this for all the classes and all the methods on the jar file. With the collected information, what we did is to analyze this textual information extracted from the names of the classes and the names of the methods. And what we did was to separate the camel case style uh, usually employed in Java. So, for example, the more files word is decomposed into two words, more and files. We did this for all the classes and all the methods names. We also clean the text if contains underscores or other types of signs that we are not interested in. And basically, this textual information is going to be fed into the vectorization step, also with the categories as a second input for this vectorization step. The first input of the vectorization step, in other words, the names of the classes and the names of the method processed as part of the previous step, is going to be fed as training into a word-to-vec model. For those of you that are not familiar with word-to-vec model, what it basically is a neural network, but a shallow neural network, meaning that only consists of an input layer, a hidden layer, and an output layer. But what is the input layer and the output layer in this case? Assuming that you have a corpus of text such as this one, the technique, what it does is that take a word as pivot, such in this case is open, and then a window of words around this pivot word. So for example, in this case, the window size is 3, so the number of words around the open word is going to be 3 in both sides. So for example, as byte source and string follow links. Then this simple technique is going to be repeated for each of the words in the corpus. And what it basically does with these words is that convert each of those words, the appearance of those words as 1 and the absence of those words as 0. So this is what is known as one-hot encoded vectors. For these one-hot encoded vectors, several of those vectors are made for the window words, and those are represented as the input layer of the shallow neural network, and the one-hot encoded vector for the pivot word is going to be the output layer. Then, through several steps of training and backpropagation, the neural net will reach an optimal value or a convergence point. When this point is reached, there are some learned weights on the neural networks, and precisely those weights will be mapped onto the words that represent the input of the neural network. And that's basically it. The output of this technique is a dictionary where the keys are the words in the corpus and the values are the vectors that represent the learned weights for each of the words in the neural network. The following step will be, once this word-to-vec model is trained, for each of the sentence in our data, meaning the names of the classes and the methods process, we are going to transform those sentences into a single vector. We did this by mapping each of the words to the word-to-vec model and then obtaining a word, a vector per word, and because those vectors contain the same size, we can do certain operations with those vectors, and precisely One of the operations we did was to get a single vector per class by averaging all the vectors um, of all the words uh, for that specific class. We did this for all the classes, but we indeed go further and for each of the vectors of the classes we average them as well, and finally we got a vector per library, and that's the final output of this training of the classes and method names, a vector per library. The second input of the vectorization step is basically the categories of those libraries into consideration. And what we did here was to discretize those categories and to assign natural numbers that represent the labels to be predicted in our data. Finally, with the transform data, the final step in this phase is going to be the actual training of the different classifiers taken in consideration. And we did consider 5 classifiers. The Bernoulli and Gaussian versions of naive Bayes, support vector machine, k nearest neighbors, and random forest. The labeling phase, as you can see, it consists of similar steps as in the previous training phase, where the names and the names for the classes and methods are extracted for a new library, the text is processed in a similar way, and the vectorization step is similar, but the only difference here is that in this vectorization step the categories are not discretized. The categories are not discretized because basically that's the main goal of this phase, to put a category to a new library. But what is similar in the vectorization step is that all the names of the classes and methods are vectorized, as I explained before. With those vectors, we fed those vectors into the train model, and the train model will output a category for this new library. To evaluate our approach, we took into consideration several aspects. For example, our data consists of 65 libraries belonging to 5 Maven categories, and those categories were HTTP clients, JSON, collections, dependency injection, and compression libraries. In this work, we do not target libraries with multiple categories. We use tenfold stratified cross-validation, and the main difference respect to the classic cross-validation is that, for example, in stratified cross-validation is also taken in consideration the distribution of the original data, because for each of the folds in the cross-validation, this distribution is tried to be placed into those folds. So for example, if the original data consists of a binary class and the distribution of this data is 80-20, this kind of distribution is going to be placed into each of those folds. Also, in stratified cross-validation, a similar number of classes or labels to predict is distributed across every fold. The main advantages of this technique is that it avoids bias, and also the machine learning algorithm is going to be trained with similar data as in the original data for each of the folds. Finally, we only consider top 1 recommendation for each of the classifiers. One of the metrics that are popular to be measure the performance of machine learning classifiers are the true positive, false negative, true negative, and false positive. I'm not going to go into the details what is considered false positive or true negative for our case. Only to mention that two the most important cases, the true positive is in our particular problem when the model is able to predict a category for a library, and indeed the category is that one. And the false positive is when the model predicts a category A and the category for that library is not A. With those metrics, we were able to compute the precision and recall. And these two figures in this slide shows that the results, the general results for the precision and recall are really good, around 80% and over 80%, which are results that denotes the effectiveness of the word embeddings and the selection of good machine learning algorithms. As you can see, precision and recall are quite similar, being the best models support vector machine, random forest, and KNN, and being the worst one, Gaussian naive Bayes and Bernoulli Bayes in both cases. But indeed, we wanted to go further and compute what is the best model out of these five models. And we did this first testing with the Friedman test, those performances of each of those models. And basically, the Friedman statistical test, what it does is that it presents a null hypothesis, that the acceptance of this null hypothesis is that there are no differences between the performances of the models, and the rejection of this test is that there are indeed differences between the performances of the models. The obtained p-value highly rejects the null hypothesis, meaning that there are indeed differences between the performances of the models. And as a post hoc test, we applied the Menji test to compute the best model. And as you can see in the figure, the worst model were indeed Gaussian naive Bayes and Bernoulli naive Bayes. But in this case, the figure presents that there are no statistical differences between the best three models because they are clustered with the same color, and their values are quite similar. So finally, we can conclude that the best three models were K nearest neighbors, support vector machine, and random forest, without any statistical differences between them. To conclude this work, we can say that the categorization of the libraries on a software ecosystem and the automatic library categorization remains as an open and an unsolved problem. Our approach tries to solve this problem, proposing a technique based on a text classification technique, where the names of the classes and the names of the methods extracted from the artifacts of the libraries within the software ecosystem are processed into vectors, and then machine learning algorithms tries to automatically perform this task of library categorization, and the obtained results were really good, and there are no statistical differences between our best models being K nearest neighbor, support vector machine, and random forest. Thank you so much for your attention, and I'm ready now for your questions.